Hi, in this in this lecture I would like to discuss about deep reinforcement learning enables joint trajectory and communication in IoT Internet of Robotic Things. So this is based on this reference paper that has been recently published IEEE Transactions on Wireless Communication 2024. Let's see the lecture roadmap. The motivation and the IoT robotic things model, ultra reliable low latency and finite block length communication, non-orthogonal multiple axis clustering, flexible SIC, successful interference cancellation, joint optimization problem, multi-goal multi-agent malcodation process, active critic deep reinforcement learning framework. So we in this paper four algorithms has been implemented: multi-agent proximal policy optimization, multi-agent deep deterministic policy gradient, multi-agent twin delayed, multi-agent soft active-stick. Code is also publicly available. Authors made the code public. See, okay, let's see the paper at a glance. The application is industrial Internet of Robotic Things. So the system has a multiple access point. Mobile users means the robots transporting materials. Static users are sensor cameras. Indoor factory with obstacles. This is the system environment. Communication downlink non-orthogonal multiple axis. Flexible successive interference cancellation decoding. Okay, so these are the methods. In this paper, mobile user, which is a autonomous mobile robo, trajectory beam antenna beamforming, downlink antenna beamforming from access point to the users, non-orthogonal multiple access clustering, decode. These four are jointly optimized. These are the four variables. What is objective is to minimize the decoding error probability, to minimize the multi-user arrival time from source to the destination in industrial environment. So these four algorithms have been implemented. Out of this, a multi-agent twin delayed method outperformed the remaining algorithms. So we need baseline models. So MAPPO, MADDPG are baselines. This is the paper at a glance. Let's see the motivation. The main motivation for this article is we have to jointly optimize the robot trajectory and communication. In this article, the authors has explained the significance of and also the interplay between the controls and communication. Control system means trajectory optimization and resource allocation. So optimizing trajectory is related to control systems and resource allocation is related to communication. Joint optimization of these both subsystems is has been implemented in this paper. So mobile robo positions continuously change during operation. Okay, dynamic wireless channel. So mobility changes channel conditions and interference. The robo is not fixed. Changes due to Doppler effect. Okay, due to Doppler effect, channel conditions interference varies. Next is ultra reliable low latency. So industrial environment requires it's a low latency application, mission critical applications like emergency situations, and also industrial manufacturing requires low latency, less than less than milliseconds, less than 1 millisecond. So trajectory communication coupling. Trajectory is related to control subsystem. Communication is related to resource allocation. This coupling. So here a shorter path may not provide the best communication conditions. There is a trade-off, and we need to balance trajectory and communication. So trajectory, beamforming, clustering, so these four are jointly optimized. Okay, so balance, reliability, communication reliability, and robo mobility efficiency. IORT system model. So it is let's in this article, an indoor factory environment with obstacles and one access point equipped with C-band antennas, and antenna users are static and mobile users. Static users are sensors. All users communicate with access point through the downlink. The downlink means access point is transmitting and static and mobile users are receiving. So mobile users must reach their destinations within the deadline. So here our one of the objective is arrival time, and avoid obstacles and avoid collisions with other mobile users. So all users are divided into non-orthogonal multiple access clusters. So let's take the model. So in 3D coordinate space, Cartesian coordinates, the location of user K at a time is, the user is here mobile user, autonomous mobile robot. Two types of users are there: xk, user k, time t, y, and also the antenna height, the height of the antenna on autonomous mobile robot, which is mu. The mu trajectory at of user k time t. So we have k mu users and k static users. So the time period is discretized into t evenly divided slots. So t max is the maximum time taken by mobile user. Okay, the starting and destination, okay, locations. Each mu is required to move from a starting location to a destination. So it moves in a curved path. So the path from source to the destination is trajectory at a speed v or velocity for a given task, ensuring arrival time. So this tk should be, the condition is less than or equal to t max. So this we will minimize. So the second object out of two, one object is decoding error probability, second one is arrival time. What is the constraint on arrival time? It should be less than or equal to a maximum prescribed time. So while the mobile user is traveling from source to the destination, it should avoid the obstacles. So delta xy is equal to 1 if there is an obstacle, 0 otherwise. Okay, so what is a predefined region? Xy antenna height. So there should be, we will define a predefined region like 50 meters by 50 meters. And similarly in disaster scenario also, disaster happens in a particular area, so that region should be specified when you are designing the environment. Let's see the channel model. Wireless. So the channel model, path loss. Okay, path loss model, Bayesian small scale fading, line of sight, non-line of sight. So this is the deterministic indoor propagation model for industrial indoor factory environment. So path loss, PTGTGR by the power of a received signal is equal to power of transmitted multiplied by gain of the transmitter antenna, gain of the receiving antenna, divided by path loss. The path loss is equal to 4 pi d by lambda whole square, as I remember basic in antenna. So this path loss dip is inversely proportional to the wavelength and also directly proportional. Path loss increases as frequency is directly proportional to the frequency and also the distance. The path loss increases with distance. Okay, and but HK is the channel vector. Okay, so path loss factor, next transmit steering vector. So this is in exponential. So theta is the angle of departure from axis point to user K. Axis point is, if you can see the diagram, this is the axis point. This is a beam forming. You can see the beam forming. So this beam is pointed towards particular user. Okay, to increase the signal strength. Okay, we need, the audience are required to refresh their basics related to antenna. So you can see here static user, mobile user, trajectory, transmit power, beam forming, clustering, all are the mentioned. This is the environment where our robots and static users are going to work. It's a production line. You can see the production line. So this is the channel model. Let's see the signal NOMA signal model. Cluster formation. K users are grouped into C NOMA clusters. So that's not the cluster assignment. This is the cluster assignment, where next is different clusters use different spectrum resources. Okay, this is the WK is a beam forming vector. Transmit power allocated to user I. So the received signal, and if you see the received signal particular user is equal to HK. HK is the channel gain, and W is the beam forming vector, SI is the signal model, Nk of T is the noise. Here the signal power is normalized. Okay, H is the uh, transpose, conjugate transpose. Okay, Hermitian. Okay, Hermitian. Noise is additive white Gaussian noise with zero mean and variance. So the beam forming constraint at axis point. So this is the constraint on beam forming. Another constraint on transmit power. So these while you are optimizing your decision, where your variables should be constrained. Okay, otherwise you cannot achieve optimal. You cannot attain optimal values. So within each cluster, users share the same resource using the power domain NOMA. Signals are superimposed at different power levels. Inter-cluster interference is avoided through frequency isolation. So you have a channel model, signal mathematical model. So let's go to the another slide. Let's see the SIC, successive interference cancellation. Okay, why we need interference cancellation? Okay, uh, users in different, okay, the each user receive unintended signals also. Okay, it has to decode and cancel the interference signal. Okay, it's in beam forming use okay, in beam forming. So let's see the decoding order. So I to k is equal to 1 means I and k are in the same cluster. Okay, so user I decodes user K signal. So user I receives both user I and user K signal from the access point. It has to decode user K signal first and cancel it, because they are both are in same cluster. So I receives, so each access point transmits particular beam for particular user. Okay, but while receiving, they receive, I receives signals of all beams of all users in the cluster. It should can decode and cancel before it decodes its own signal. Next, otherwise 0 means, so I2k of t is equal to 0 means, uh, okay, here are the same cluster user I decodes is a next condition. Okay, user I decodes his own signal. Okay, uh, I2k of t is equal to minus 1. Users I and k belong to different clusters. Okay, so it's a decoding order. So you can understand this more by studying in detail. So what is the constraint on this decoding order? Okay, this value should be less than or equal to 1. So this is the decode if this is proposed by the authors in this paper. So why you need a decoding order? Okay, so if you understand why we need interference cancellation, successive interference cancellation, okay, then you can understand the decoding order, because we are clustering the users, and users in the same cluster receives unintended signals of other users in the same cluster. Okay, so you should specify the decoding order, otherwise the users, okay, find it difficult, okay, difficult to decode, okay, and cancel interference. So let's see SIC interference and signal to interference noise ratio. When user K decodes his own signal, okay, the decoding order, see HK. So here signal is normalized, okay, that's why we S is removed, the received signal you have, okay, this is the interference. So gamma is SINR, signal to interference noise ratio. H is the channel gain, beam forming vector divided by interference, plus sigma square is the noise, sigma square is the noise, okay, for all k t. So when user I decodes, so this is the formula. So final you can see this is the SINR. So this decoding order enables adaptive interference cancellation, improves reliability, fairness, and overall performance. So this is one of the contribution by authors in this paper. So you can read this in detail, okay, by taking more examples. Let's go to another. So finite block length, ultra reliable low latency, okay, communication, okay. So early, according to Shannon, infinite block length is used. However, in this application, finite block length is very important. So let's see. So here we will define what is throughput, what is decoding error probability. Okay, so this bit error rate. Okay, so these are the important basic equation. Okay, so let's understand what is throughput. It is the formula, okay, explained by Shannon. So log 2 of 1 plus, okay, gamma is a signal to interference noise ratio, and V is the channel dispersion. So capacity, okay, conventional achievable throughput calculated by Shannon, the great scientist. Okay, capacity. So Q function for a given transmission rate, d by m bits per seconds per hertz, the downlink decode error probability of user k, okay, is equal to, this is the formula. Okay, so here our objective is to, okay, minimize the decoding error probability. So another objective is minimize the arrival time. So this so when you minimize decoding error probability, throughput increases. Okay, throughput throughput depends on signal to interference noise ratio. So you can so when you minimize the errors, so minimizing errors means reducing cancellation, interference cancellation, increasing the signal strength. Okay, so next automatically throughput is the function of signal to interference cancel ratio, SANR. So the objective is achieved. Our objective is minimize. We cannot directly reduce the error probability. How you can reduce it? You can reduce it by increasing signal strength, reducing interference. Okay, interference. Overall, the ratio signal to interference noise ratio increases, and if it increases, throughput, achievable throughput, okay, also increases. Okay, let's see the joint optimization problem. Optimization is the variables, the decision variables. L is the trajectory, downlink beamforming, NOMA clustering, SIC decoding order. So these four variables are optimization variables. So when you because these four variables decides your objectives. You cannot directly minimize the decoding error probability and directly minimize. You cannot directly. It is an indirect approach. So these variables, so four variables decides your objective. Cannot directly reduce. Okay, you need to select the optimal values of these such a way that your your decoding error probability is minimized and arrival time is also minimized. So trajectory, if you see, it is a source to destination, and we have location. Okay, this is the curved path. Beam forming is done by axis point. Clustering is done at the receiver. So these two are at receiver. Okay, trajectory depends on mobile. So beamforming is done by axis, but let's see who does what. Okay, trajectory is related to the autonomous mobile robot, beamforming is related to axis point, clustering and SIC decoding order are done by the static or mobile users. So any optimization problem has objective, and either it can be minimized or maximized. So if you apply common sense, error probability should be minimized. So if the error probability is minimized, reliability increases. Okay, arrival time minimizes, latency is also minimized. Let's see the optimize. Each objective has constraints. So these constraints, or some of the constraints, are related to mobility, and some of the constraints are related to multiple axis technique. Okay, and a successive interference cancellation constraints, and another is related to beamforming clustering. So we have four trajectory. Okay, so these four decision variables have constraints. Constraint means for constraint. Okay, then your objective is achieved. If you don't constraint, you don't apply the constraints. Okay, then your value, okay, optimized value, we are trying to find out the optimized value, whether it can be minimum or maximum. In this case, it is minimum decoding error probability and minimum arrival time. So as you can see, the first initial position LSK and destination, okay, LDK, TK is the time taken by the mobile user to reach the destination. I can see that Next 7J constraint, maximum movement constraint, which is velocity is equal to distance by time. So location location t minus 1 less than equal to V max. Okay, how to avoid the collision? Okay, you need to impose some constraints. Okay, so LKT. Okay, how you avoid collision? So when collision occurs, two users, okay, two users will be at same location in the Cartesian coordinate space. So if I impose a constraint where K is a user at time t, K dash is another user at time t, their location x, y, okay, is not equal. Okay, they are not equal. So if you impose these constraints, you can avoid the collision. So maximum movement, okay, so you need to set the speed limit. Okay, next, same cluster beamforming constraint. Okay, norma decoding requirement. So next is decoding order. Okay, next is so these are the constraints. So if you understand basic optimization theory and also basic communication theory, combining these two, then you can better understand what is optimization, how it can be applied. And robotics, we just have to understand what is mobility. So mobility, again, it can be a robo or mobile robo, or can be a UAV or mobile user equipment. Okay, mobile phone. Okay, why the problem is difficult? So traditional optimization, okay, non-convex and integer optimization. Okay, so we have to jointly optimize trajectory beamforming, clustering, successive interference cancellation order. Okay, these next next objectives are mutually conflicting. These, okay, you need to find a trade-off. If you try to decrease decoding error, what happens? Arrival time increase. You have to find a sweet spot. Okay, a balanced value. So that is the difficulty. Strongly couple optimization variables. So these decision variables, clustering, informing channel context, trajectory, SIC, decoding order. Okay. Next is dynamic. As mobile user is moving, then channel is also dynamic. So now this problem is difficult to solve using traditional optimization techniques. Then we use we model it using partial observable Markov decision process. So again, RL theory, reinforcement learning theory. So what is state, action, reward, transition probability, discount factor? Okay, so yeah, we have three theories: reinforcement learning theory, communication theory, control theory, and finally optimization theory. Okay, so now the research requires multidisciplinary knowledge. Okay, so if the algorithm works, then again you may have to implement on FPGA, and if it works, you may have to design the IC. Okay, application specific integrated circuits. Okay, let's see what is a state. So okay, state, each agent distinguishes current state according to its location. So I define goals. One is mobility, because we are jointly optimizing control and communication. One goal is related to mobility, okay, and another goal is related to communication. So in goal one, we try to minimize, our objective is to minimize arrival time. Goal two, we try to minimize the decoding error probability. what are my actions? So we do, okay, two agents, okay, one is mobility aware agents and is communication aware users, okay, goal 1 and goal 2. Let's see mobility aware user. Okay, this is the action. You can see action is depending upon location. Speed constraint, okay, the difference should be less than or equal to maximum velocity. Next, communication aware actions or trajectory beamforming and clustering. This L, okay, this small L, Italian Greek L is loma clustering. Alpha I to J is the decoding order. Okay, speed constraint. So you need to define what is a state, what is an action, okay, what is your optimization objectives, what are your decision variables, and how these and what are the constraints on these decision variables. Let's see my reward. So this is very important. Without reward, DRL need to design the reward function for a specific problem. So designing reward, okay, designing your state, okay, designing your action space is very important if you want to apply deep reinforcement learning, okay, to your problem. Let's see what is my reward. What is the what is it? So reward should be in a limit, okay. You need to penalize. There are collisions, okay, okay. So -1 to 1. How I design my reward depends, okay. uh, okay, if you don't design your reward properly, what happens? You, okay, let's see the L and location of, okay, location and time t, destination or goal, okay. Here I have include other if n belongs to communication. Here we have two goals. Goal 1 is related to communication, goal 2 is related to mobility, because we jointly optimize the control system and communication. Okay, epsilon is a decoding error probability. So reward cannot be less than -1. So okay, it's a closed brackets, okay, not open, means the maximum value is 1, minimum value is -1, okay. How this is my how I need to design reward in such a way that I have to penalize, okay, for bad actions. I have to give, okay, reward to the good actions. Okay, but remember the goals of our agent. So this is how I design my reward, how I penalize collisions. So these again equally depends on location, epsilon, decoding error probability. Okay, a subject expert can design a reward. Okay, so these are the algorithms. Okay, according to authors, multi-agent twin delayed has outperformed the remaining baselines. What is a baseline? You need to compare your best performing algorithm, okay, with other performing algorithms, and when you compare, remember the comparison should be fair. So here it's a simple, according to the paper, one of the limitation is a simple mobile user model has been taken. Okay, what is a more realistic mobility model is you need to, the state depends only on position. So if you want it to be more realistic, velocity and acceleration should also be considered. Okay, when you're designing state, your state should include position, velocity and acceleration. Okay, the current paper, fixed height, okay, position, height, movement, state variables, velocity, acceleration, constraints, decision. Okay, if you want it to be more realistic, okay, the position an antenna height can be fixed or modeled dynamically. Okay, and next, the movement representation, okay, position obtained from velocity and acceleration. So explicit VA state, and in state design, velocity and acceleration should be included. Yes, this is a limited simple model. Okay, so let's see the simulation setup. So this is where we need to define the factory. It's 50 meters by 50 meters. You can see you have a the mobility unit. Here the one it's not a drone, can be applied to drone, but here we consider, in this the authors consider more autonomous mobile robot. You can see the gray boxes, gray triangular boxes, all the obstacles. So height of the antenna I assume to be 1 meter, multiple axis. Okay, the network we have 2 4 6 for different 2 users, 4 users, 6 user, mobile user 1 2 3, class number of class 2 to 3. Let's see the number of bits, packet size 100 bits, 50 symbols. Next, maximum time is 2000 seconds, and noise power spectral density is minus 100 dBm per hertz. Okay, and what are the values of mobility? 5 meters per second. Okay, maximum transmit power is 0.02 to 0.1 transmit power, and my x max, y max is 50 comma 50 meters. So why? Because you are trying to, your state includes position. What are the values of that position, and what is the maximum value? Here we have to define. See, okay. Next is exploration, noise, scaling factors, in deterministic policy gradient. These are the values. You can see. So when you are implementing deep reinforcement learning, what is my activation function? In actor, it is tan h. In critic, it is rectifier linear unit. What is my optimizer? Adam. So you have different optimizations. Okay, Adam. Okay, and stochastic gradient descent. Okay, so let's assume decision update is 1 interval is 1 second. However, this is not practical. Authors said in this paper. Okay, in URLLC, ultra reliable low latency communication. Actually, this decision update interval should be in milliseconds. So, what is my discount factor? It is 0.9. So, how these values are defined? These are the parameters, hyperparameters. These are hyperparameter values are defined by trial and error. Okay, for which values multiple hours of days, months of simulations. Okay, so okay, so if you use these values, these are optimized values of DRL implementation. Okay, buffer size generally it is base size 128. Okay, how I am telling the value for this? These are called hyperparameters. The algorithm designers, when they implemented, they by using trial and error. Okay, okay, trial and error. Then they define some values. Okay, which can be generalized. So if you want, you can tune 0.97. You can see. Okay,